This webinar will cover copper foil basics, copper profile measurements, hammerstad and Jensen and Sonnet software correlation, Hall-Huray Snowball model, copper foil data and images, differential insertion loss measurements, and modeling. Today's speaker is Alan Horn. He holds a bachelor's degree from the Syracuse University and a doctorate from MIT, both in chemical engineering. Since joining Rogers Hall-Huray R&D Center, he has worked on the development and testing of ceramic powder-filled high-frequency circuit substrates. He is an inventor and co-inventor of 16 U.S. patents in the area of high-frequency dielectric materials. Before joining Rogers, he worked at Dow Corning on silicon thermoplastic materials and Arco Chemical Company on polymetric oil-field chemicals. So at this point, I will hand the presentation over to Alan.
Yeah, thank you, Pat, for that kind introduction. First, I'd like to acknowledge my co-authors, Pat LaFrance and Chris Case, here at the Hall-Huray R&D Center, that really do all of the work that happens here. John Coonrod is a marketing development manager who does all of the, all of the highest frequency, the 110 gigahertz measurements, and Bruce Fitz is our copper foil expert. Pat had basically covered this. This is like one of our, one of my favorite subjects. We'll be, again, talking, as Pat said, about copper foil, basics and profile measurements, the different correlations and models, and then look at some real data and images on copper foil, and then look at actual measurements on circuit performance, and hopefully draw it all together with the conclusions. Yeah, first I'd like to make clear this paper is presented from the experimentalist perspective. As Pat had mentioned, my background is in chemical engineering, so I have something of a practical rudimentary knowledge, the electrical engineering involved in this, but it is again, predominantly from experimentalists and materials. So what we're going to demonstrate is that the RZ, the peak to valley, and RQ, which are RMS, copper profiles alone do not describe copper performance adequately, which is something that's implicit in the Hall-Huray model. That the nodulation or snowballs in the copper foil treatment are what increases loss, not height variation. However, if your RQ is not a bad measure if only foils treated for circuit applications are concerned. We'll discover that nodular low-profile foils most closely resemble the modeled surfaces, and that dendritic foils deviate farther from the model structure. Now, one of the interesting things that has come out of this is that in spite of exhibiting measurable profile that is predicted by all of the models to increase loss at higher frequencies, rolled foil loss values match smooth conductor values out to 110 gigahertz. And the other thing we'll discover is that with some adjustments to RQ or surface area index and nodule radius, as from what's measured by white light interferometry, both the Hall-Huray model and Sonnet surface inductance correlations can fit measured insertion loss data perfectly out to 110 gigahertz. So first, a review of some copper foil, as there are two methods of manufacturing copper foil. The rolled process, as it implies, actually starts with about a 15-centimeter thick billet, which they can roll out to a thickness of between 17 and 35 microns with two beautiful, with a mirror finish on both sides, out to many hundreds or thousands of meters. But, additional nodulated treatment, at least for applications where it's going to be used instead of circuit substrate, additional nodulated treatment is added by a plating process to improve adhesion, to the PCB. And this is, historically the lowest profile and lowest loss foils for PCB laminates, and they've been used in RF laminates to squeeze the last ounce of, high loss out for the last 50 years. Yeah, the electrodeposited process is more economical and in more widespread use for printed circuit foils. In this case, where they start with copper raw materials, I've actually been to the copper plant and seen miles of overhead power distribution wire coiled up in the back lot. It's dissolved to make copper sulfate and then plated onto a slowly rotating polished drum. It's up to something like 2 meters in diameter and 2 meters wide. And then the plated foil is then taken and further treatments are added, again for printed circuit applications. Historically the bath side of the foil had been plated to increase the roughness, to increase adhesion, and the additional surface treatments were plated onto the bath side. In more recent years, the plated foil manufacturers have gone to a reverse treated process in which they now try to make the bath side as smooth as possible and plate the treatment for adhesion to the circuit substrate onto the drum side so it more closely mimics rolled foil. As I said, there's another newer development they call battery foil, which is even smoother on the bath side, and we have actually seen experimental reverse-treated and battery foils with treatments that are as low or lower in profile than rolled. Okay, for copper profile measurements, again, for many years, mechanical stylus contact profilometry is a standard tool for surface profile measurements. This produces a 2D surface image of the surface topography. White light interferometry produces a 3D image. The white light interferometry instruments have become common in the last decade. And the commonly reported variables that can be calculated from either measurement system include like R to Z, or RZ, the peak to valley roughness. RQ is the RMS roughness. And then surface area index is somewhat illustrated by a souvenir mug I got at a bicycling trip years ago. And that essentially, quantifies the, additional surface area per unit surface area caused by the roughness. So this is the surface area index. So this drawing illustrates the mechanical stylus profilometer. The probe stylus rides over the surface. There, as you might imagine, it in fact has a dimension which can be of the same order of magnitude of the dimensions that you are measuring. So as it shows in this location, that gives something of a compressed value since it doesn't go all the way to the bottom of the valleys. The white light interferometer, there actually seems to be to defy physics, but not really, in which it is able to look at dimensions that are considerably smaller than the wavelength of light by using interferometric patterns and with a very closely calibrated stage that moves, and by measuring the change in the interferometry patterns, is able to generate the surface topography in about a millimeter squared area down to about a nanometer, about 1 nanometer resolution. So in this current picture, we're looking at the output from the white light interferometer. This is for the treated side of one of our high-profile ED foils. You can see that on the right is generated a 3D image, and from these, from the interferometry pattern, that calculates the RQ, the RMS roughness, the RZ value, which you'll see is considerably larger, and then also the surface area index. In the following slide, we're looking at now the other side of the same ED foil. So this is now the side that was against the drum. You'll see that the RQ is considerably smaller. The RMS roughness is less than a fifth of the value, and similarly, very low RZ, and the surface area index is very close to 1, meaning that it's actually, behaving as if it's perfectly smooth. Certainly one legitimate question is how the mechanical profilometer data would compare with white light interferometry. And in this next slide, we answer the question, which is, I guess, to be not terribly well, but not terribly badly either. So what we've plotted here on the y-axis is the WICO, the interferometry RZ value, and compared that to the manufacturer's mechanical profilometry. This is for one grade of ED foil on the treated side. If the measurement systems were perfect, the data would lie on the y equals x line. You can see that, as we had guessed, that the values are higher for the profilometry, and also that the data is more compressed, as we expected for the mechanical profilometry. So while the mechanical data spans from just a little less than 10 to a little over 12 microns, the white light interferometry covers a range from about 13 to 18. But at least one thing that's reassuring is that they are all in the same ballpark. Okay, now so how the copper roughness values affect the performance of the circuit substrate. It's been known that conductor roughness increases loss since the early days of waveguides. And so this was first modeled in a paper and numerically hand-integrated by Sam Morgan and Bell Labs in 1949. This Morgan or Hammerstad model was adapted by Hammerstad and Jensen along with correlated data in an IEEE paper in 1980 for modeling microstrip performance. And this correlation factor is based on the ratio of the RMS profile of the copper to the skin depth at that frequency applied, and then this correction factor is applied to the calculated smooth conductor attenuation factor. So what you do is at frequency, calculate the attenuation factor for the smooth conductor, and then multiply it by this correction factor, which is a function of the RMS, roughness of the copper to the skin depth at frequency. If we plot this, conductor attenuation factor, against frequency for a range of roughness values from about 0.2 micron RMS to 3 micron RMS, which covers about the total range of commercial copper foils that you'll see, is you get traces that look like this. Again, you can see in the gigahertz sorts of frequencies that most of us are working in that they're in fact, that this correlation predicts an increase in attenuation factor with roughness. Then also from the mathematical form of it, it predicts that it will plateau off or that it will saturate at a value of 2. So again, according to this correlation, the rough conductor wouldn't be any higher attenuation than twice that of smooth, although we will see going forward that that is not true. However, in years past, it had been true, as it works very well over the range of parameters that was commonly used in microstrip circuits prior to 1980. So right now we're looking at the insertion loss of 50 ohm, 50 ohm transmission lines on 0.5 millimeter thick GR laminate, which is dielectric constant of 2.2 and dissipation factor of 0009. And this was about the full range of copper foils from 0.4 micron RMS to 3 micron RMS and up to 10 gigahertz. And we see that the range of insertion loss values that are measured are actually bounded very well by this Hammerstad and Jensen correlation for the smooth foil on the low loss side, and for maximally rough or twice the conductor loss, on the high side. Okay, another correlation is from Sonnet Software. It's based on a joint paper with Rogers. It was presented at DesignCon in 2010. And based on that work, Sonnet Software has developed a correlation between the RMS roughness of copper foil treated for PCB laminates and excess surface inductance. This is something embedded in the Sonnet software conductor model, so I don't really understand exactly how it works. However, I can tell phenomenologically that it predicts both the effect on attenuation constant and propagation constant with good accuracy. And the propagation constant effect is manifested as an increase in the apparent or the effective dielectric constant of the microstrip line with increasing copper profile. Yeah, so these are both insertion loss and K-effective data that have been that are both measured and predicted by the Sonnet software correlation, so that we get excellent shape on different thicknesses, and over a fairly wide range of frequencies. Okay, the Hall-Huray snowball model is actually derived on first principles from calculating the scattering and absorption of stacked snowballs, which resembles the nodules on treated foil. It's been incorporated by several commercial EM software packages. And one drawback is this only addresses the effect on attenuation constant, not on the propagation constant. Mathematically, it works very much the same way as the hammerstad and Jensen, that you calculate the attenuation factor for the smooth conductor and then apply the Hall-Huray correction factor, which is based on the ratio, or is based on the surface area index and the ratio of skin depth to the nodule radius. Yeah, so here are some calculations. The solid lines being the hammerstad and Jensen model for for three different foils with these parameters of roughness and surface area index. So these are the black lines, red lines, and blue are each for the same foil. As you'll see, or as we had discussed earlier, the hammerstad and Jensen all saturates at a conductor attenuation factor increase of a factor of 2, while you see that the Hall-Huray predicts a much higher increase and is clearly not saturating in it all the same way. Yeah, there's also other modeling and correlation approaches in the literature. These other authors have proposed, correlations that we weren't able to include in the present study. Two that address the effect of copper profile on both attenuation and propagation are by Yuri Shotnev and then also Marina, that were presented at DesignCon in recent years. So now we're looking at white light interferometry data on both the treated and untreated side, a very wide range of copper foils, varying from RMS roughness values of 0.2 to up to 3, surface area indices from perfectly smooth to nearly a factor of 4, nodule radii from, non-existent in some cases to from 0.2 microns up to close to a micron. And then looking at the untreated side, as we'll see in the photographs, these structures are quite different, but there still can, particularly in the case of some of the reverse treated foils, be significantly, can have significant roughness values. So in fact, if we look carefully here, the RQ value of the untreated side of this particular, type of reverse treated foil is actually higher than the treated side. Yeah, so here's some of the copper foil images. These are taken at 7,000x on a scanning electron micrograph. You can see this is on the treated side of the reverse treated and rolled. You can see the striations in the rolled, which is actually the plated treatment following the structure that was left behind from the rolling process. And you can see with the various different grades of foils, you can get quite a large range of nodule diameters. And if we look again at the same magnification, and these are the same foils in the same locations, you'll see that the structure looks quite different. They are now nodule-free. Again, if you're looking carefully at the roll, you can see the effect of the rolling process in aligning the copper grains. That this is looking at the bath side of the reverse-treated foil that exhibited a very high profile. And you can see now, instead of seeing lots of small nodules, what you see is kind of a long-range periodicity of like treeless mountains. And like I say, and as we'll discover in the data going forward, it's the short-range periodicity of something like the nodules that affects the insertion loss and the propagation, and not this long-range periodicity of bare mountains. Now, finally, here the treated side is some of the other of the three of what we call the dendritic foils. So again, rather than having small nodules that really resemble the snowballs as in the Hall-Huray model, these look more like perhaps deciduous trees or evergreen trees. There, and then lastly, a special experimental foil with a very interesting structure. Okay, now we'll get finally to making some electrical measurements and showing the data. Yeah, in this case, we're looking at 50-ohm microscript transmission lines that have been etched into 3 Rogers low-loss laminate materials with dielectric thicknesses from 2 to 7 mils. RO3003 is an RF laminate. It's a PTFE silica composite with a dielectric constant of about 3 and dissipation factor of 0.001 at 10 gigahertz. The RO1200 digital laminate is a silica PTFE and woven glass fabric material with a dielectric constant of about 3.1 and DF of 0.016 at 10 gig. And Ultralam 3850 HT flexible laminate is LCP, which is a pure polymer material with a dielectric constant of 3.1 and dissipation factor of 0.002 at 10 gig. Yeah, so the differential and insertion loss and phase length calculations, what we do is calibrate to the cable ends. We then measure S21 magnitude and phase on both long and short transmission lines, divide the difference in magnitudes by the difference in length for differential insertion loss, use the differential phase length calculation to calculate the K effective of the microscript transmission lines, and finally use the K effective and circuit dimension data to extract the dielectric constant of the substrate. They're using various different models. Yeah, so in the following studies, what we'll see is that rolled foil shows the same loss as smooth out to 110 gigahertz, even though it's rough enough that the models predict that an increase in loss should occur. And we'll see that with some adjustments to precise values in the surface area index, nodule radius, or RMS roughness, both the Hall-Huray and Sonnet models show excellent fit to measure data out to 110 gigahertz, as long as the treated side of the foil is the one facing the dielectric. Yeah, so here's 50-ohm transmission line performance out to 110 gigahertz on 5 mil 3003 laminate. The red line is what was measured, on a circuit fabricated with rolled foil. The blue line was what was measured on one of the ED foils that exhibited an RMS roughness of 2.2 microns, surface area index of 3.9, and a nodule radius of 0.4. I said the number or the values for the rolled foil again is there's a measurable roughness value of 0.4 micron RMS, surface area index of 2.1, and a nodule radius of about 0.3 microns. But we see that it actually fits the modeled smooth data absolutely perfectly out to 110 gig. If you go with the hammerstad and Jensen and Morgan correlation, just inputting the value of 2.2, which is the RMS value for the blue, for the copper that was used in the measurements for the blue line, you'll see that it falls considerably short of the law of predicting the loss, particularly at high frequencies. You see with the Sonnet model, if you input a value of 2.6 micron RMS, instead of the measured value of the 2.2 RMS, you get an excellent fit of modeled to the actual measured. And with the Hall-Huray model, if we use the surface area index that is measured by the white light interferometry, if we reduce the nodule radius value, again, we get nearly a perfect shape and a fit out to 110 gigahertz. So now we're looking at similar data, again, on 5 mil laminate. This is the RO1200, which was the slightly higher loss PTFE silica glass fabric reinforced material. Again, the rolled foil. With these parameters, again, the same, now a different, reverse treated foil sample that has an RMS roughness of 1.2 microns, surface area index of about 3, and a measured, nodule radius of about 0.4 microns. Again, we see that the rolled foil actual data, the red line, fits the modeled smooth just perfectly. And again, with slight adjustment to the RMS value from 1.2 to 2, we get excellent fit with the Sonnet model. And also, again, using the input value of the surface area index, if we reduce the input value of the nodule radius from what was measured at 0.4 to 0.15, we get excellent fit of the data out to 110 gig. Yeah, the performance of the rolled foil we find to be quite intriguing, so that we've looked at that in a number of different ways. In this case, we're now looking at 2 mil, at 2 samples of 4 mil, and a 7 mil laminate. These are all on the UltraLam 3850 LCP material. And again, you can see what we calculate, for absolutely smooth foil, for the 3 different thickness values, fits the data quite well. Yeah, so now we'll compare, the performance of 3 foils again, which will show the pictures here. Here are 2 of the dendritic electrodeposited foils with the high profile treatment. It have a fairly large nodule size of about 0.9 microns, a fairly small nodule size of about 0.4 microns, and then looking at the rolled foil again with the considerably lower surface area index and small nodule size. And you can see again we get perfect agreement on now 4 mil UltraLam LCP laminate with the rolled foil and modeled smooth. And again, the magenta and the blue lines are for the 2 ED foils with about the same surface area index, but the increasing nodule size. And again, if this was now looking at the Hall-Huray model kind of in the other direction, putting in the, using the measured nodule size as the actual input, and then, adjusting the surface area index to get a good fit with the modeled and measured data. So you can see that the Hall-Huray model, in fact, has a reasonable, that the changing the input nodule size to what was measured, can explain the difference between the performance of the 2 foils, as long as the surface area index value is reduced to get a good fit. In this case, we're looking now at the performance of the Sonnet model along the same way, and you can see actually in this case we get very good agreement there with the Sonnet input value of 3 microns RMS with the 3 micron RMS foil. So now we're comparing the reverse treat foils, treated and untreated sides. So one of the nice things about working in microstrip is you can kind of isolate the effect of which side of the copper that you're looking at, as long as you can get good enough adhesion to be able to make a measurement. So in the following slides, what we'll see is that the untreated side of reverse treated foil can have a high RMS roughness value, but this with the different non-nodulated structure compared to the treated side, and we'll see that it's the nodules that increase loss and affect the propagation constant, not the RQ alone. So remember what we'll be comparing here. This is the treated side with the nodules for this certain half-ounce reverse-treated medium profile foil. There is a similar grade, but at 1 ounce. These were the measured values of RQ. And in particular, on the 1 ounce, you'll see that the RQ in the treated side is 0.9 microns, which is less than the measured RMS roughness of the untreated side, but again with this very different structure. And now it said we had made laminates with the treated and untreated sides facing inward, and measured the performance of 50 ohm lines on them. The solid black line, once again, is for the untreated perfectly smooth foil modeled. It's actually quite close in performance to the untreated sides, even though the roughness was as large or larger. And you see that the nodulated sides exhibit considerably higher loss, and in fact are matched by the Hall-Huray model with these input parameters. So in this slide, what we've done is to kind of reduce the performance to a single figure of merit, look at the insertion loss of 50 ohm transmission lines measured at 50 gigahertz, and then plotted this against the RMS profile of the conductor surface facing the dielectric. When the treated side is facing inwards, which is where the electric field is concentrated, you see that as you increase the RMS profile, the insertion loss increases, but with the untreated side in, so now kind of the bare mountains without the nodules on it, we see that there's much less effect of the surface roughness on the insertion loss. So now, in previous work, we'd found an unexpected effect of the copper foil profile on the effective dielectric constant of transmission lines in microstrip, with the effect being largest on thin laminates. So the data that we have here is what the K effective of the microstrip was as a function of frequency, all on 4 mil LCP laminate, just with copper foil roughness varying from 0.5 micron RMS to 3 micron RMS. So the only thing that's different here is the roughness of the copper foil, and you can see that there's a substantial increase, about 15% in the K effective value. If we then take these values and the circuit dimensions and use, in this case, the hammerstad and Jensen model to extract what the dielectric constant of the substrate must have been, you see for the smooth copper, we get a value of close to 3, which is what the actual dielectric constant of the material itself is known to be, and then we get about a 15% increase with the highest profile copper foil. So again, one way of looking at that is we're now looking at the dielectric constant value for the substrate that was extracted from dimensions and from the K effective. This was looking at the reverse treated low profile foil on 4 mil LCP laminate. You can see with the treated side in, the dielectric constant extracted dielectric constant is about 3% higher than with the treated side facing out. So again, it's the nodulated treatment that's affecting the propagation constant and not the roughness itself. And that's also further demonstrated in this side, where similarly we're looking at the RMS profile of the conductor surface facing the dielectric. And now the effect on the extracted dielectric constant, based on the phase length. You can see that as you go, for the treated side facing in, that is the nodules facing the dielectric, there's a substantial increase in the extracted propagation constant with roughness, but with the with the reverse treated and rolled foils, with the untreated side facing in, there's actually very little effect. So increasing non-nodulated surface profile has little effect on the propagation constant. That one actually, an interesting note, and so what we hope would be a bright spot in future materials developments is the best of experimental ED foils are approaching the performance of theoretically smooth copper. Of course, for it to have to be a practical laminate, you need to have good adhesion that is preserved through the both circuit processing and end-use processes. So I guess we are still all working together to straighten those out. As I said, but we are seeing very good performance for low-loss ED foils. So this brings us to our conclusions. I said, yes, it was obvious from the photos and measurements that copper foil structures can vary widely. With small adjustments to white light interferometry measured profile parameters, the RMS roughness for Sonnet, or surface area index, and value of A, the nodule radius for the Hall-Huray Snowball model. You can get excellent agreement for both measured and model insertion loss curves out to 110 gigahertz at the very least. Now we're considering reverse treated foils. The loss is affected by the profile of the treated or nodulated side. So changes in profile surface area index of the untreated side have a much reduced effect on loss, and that there's a similar effect of nodulation on the propagation constant, the extracted dielectric constant of the substrate, the profile of the nodulated side causing a larger effect and non-nodulating having little effect, and then happy conclusion that rolled and experimental foils are in fact approaching smooth foil insertion loss. And that brings us to the end.
Great. Thank you very much, Al. Excellent presentation. Good source of data there. So we'll start the Q&A session now. The first question is, what is Roger's experience in dealing with various software modeling suppliers regarding their interest in this info to provide accuracy?
Well, of course, everybody is interested in this. The logistics. Well, first of making sure that everything is accurate. As we have a wide range of foils and thicknesses to consider, and the precision of these measurements is not quite the same as the precision of the dielectric constant data that we're used to for RF laminates. So we are working through all of this, and hopefully, we'll be able to implement this, sometime in the near future. I know that John Coonrod in particular is working on incorporating these models into our impedance calculator, their MWI, which is available on the website. So, that will kind of be our beta test site to actually implement the Hall-Huray model into the impedance calculator as a roughness effect, and hopefully develop a database that will allow us to go forward with the commercial guys.
Great. And would this information be applicable to the apparent/design decay?
again, for the MWI calculations, that is something that John is in the process of implementing, and for the commercial software from people on the outside, it becomes somewhat more difficult because it has both the copper roughness and the laminate thickness effect. So, I mean, that will likely be addressed through a separate white paper.
Okay, great. Next question, what would be the lowest loss gold plating structure for a wire bondable RC boards?
Wait, come again?
What's the lowest loss gold plating structure for wire bondable RC boards?
Oh, the surface finishes is something that we hadn't addressed here. I think it's one. Again, for PCBs, a very common finish is the electroless nickel immersion gold, I believe for wire bondability also, but that in fact does increase the loss quite substantially at higher frequencies. So yeah, I am not sure how that's addressed.
Okay. Does the Sonnet implementation of the hammerstad also saturate at an attenuation value of 2?
I don't. No, the Sonnet model does not saturate. It predicts the values that we see up to up to the 110 gigahertz. It shows the similar effective frequency that the Hall-Huray model does.
Okay, great. Does the Hall-Huray model go into any detail describing the effect on surface/sheet resistance of the surface roughness?
Well, so actually, a number of the original papers are beyond my ability to comprehend, all of the implications of it. But yeah, that is, in the papers that are developing this final, fairly simple correlation, all of the theory is covered. There have been several PhD theses that have led to the development.
Okay, and this one. There's a lot of questions here on, what the manufacturers report. Do they certify the RMS SAI when you purchase the laminate and other things that affect the surface roughness and weight?
Well, sir, no, again, we certify that the types of foils that are used are controlled and, say a part of the part number there, but we have not advanced to the point where there's actually a specified range of surface profiles, for all of the varying grades of copper, largely because the copper manufacturers mostly still report the data just based on the, just the RZ stylus.
Okay.
Which is, a somewhat limited utility. Again, one of the things that we have noticed, though, is, if you go to lower profile foils, there's also lower variation in the profile. And so we get more consistent data as well as lower loss with the low profile foils.
Okay, next question. Can this system be correlated to round conductors used in coax?
Oh, I imagine it can, but I don't know. Again, that's outside my area of no idea.
Okay.
Yeah, but no, I would imagine, again, since it is largely skin effect, it probably would work in a fairly simple implementation, say.
What's the best method to measure surface roughness and other attributes?
Oh, I said, the white light interferometry is what seems to correlate most with both what we measure in terms of electrical performance and what we see when we look at it with the scanning electron microscope.
Okay, and what category would the Rogers Low Pro copper fall into for surface roughness?
So that's reverse treated foil, and that's the 0.6 or 0.7 micron RMS range.
Okay, next question was, you showed differences between the hammerstad at high frequencies and the Hall-Huray. Which is there one that's better than the other for that?
Oh, sure. Yeah, we believe that the hammerstad correlation grossly underpredicts the effective loss or the effective conductor roughness at higher frequencies and on thinner laminates. Yeah, so in this case, it's the Hall-Huray or the Sonnet models that are the accurate predictions of conductor effects, as long as you adjust the precise input values.
Okay, great. I think we've pretty much exhausted the questions here. Thanks for a great presentation, and thanks to Rogers Corporation for sponsoring today's webinar. You can find out more about their products at rogerscorp.com. This webinar has been recorded and will be available in the events section of the Microwave Journal website in about 24 hours. Anyone who registered for today's session will receive an email with a link to download the slides, so those will be available to you later on. And we thank everybody for joining us today.